Hello again. Just want to take a few minutes to go through the examples from the first derivative test notes that we did not get through during class. I believe there are four of them. No, and let's go through these real quickly. The first one, given a function, we want to identify the intervals where the function is increasing, decreasing, and state any relative extrema. So again, we can find if a function is increasing or decreasing by looking at the sign of the derivative. So if the derivative is positive, that means the function's increasing. If the derivative is negative, that means the function's decreasing. Now, the only way a derivative can change from positive to negative is if it goes through zero. So we're going to set our derivative equal to zero and find out what x values make the derivative equal to zero. And those x values are going to be our critical numbers. So we get x equals 2 as a critical number. We're going to put that on a sign chart. And on the bottom, I'm going to put the sign, positive or negative, of the derivative. That's going to tell me what the function is doing in terms of increasing and decreasing. So if we plug an x value of 0 into the derivative, we want to find out if the derivative is positive or negative. A lot of times it's easiest to plug it into the factored form. If you put a 0 in for x, you have a negative 8 times 4 is a negative number. It's going to be negative 32, but really I'm interested in the fact that it's negative because since the derivative is negative, that tells me that the function is decreasing. And if I pick a number above 2, say 3 or 4, plug that into the derivative. 3 cubed is 27, minus 8 is going to be 19, positive 19 times positive 4 is going to be a positive number. Tells me my function is increasing. So in terms of answering the question, we know f of x is going to be increasing on the interval from 2 to infinity. And it's going to be decreasing on the interval negative infinity up to 2. And we have a relative minimum because the derivative changes from negative to positive, a relative minimum at x equals 2. If we want an ordered pair, plug 2 into the original function, you get negative 44 as a y value. So you could say there's a relative minimum at 2 comma negative 44. Doesn't say it's to state the x value of the relative extrema, just state the relative extrema. So the ordered pair is probably a better answer there. Okay. All right, scrolling down, we have this f of x equals a cubed, or the square root of 3 times sine x plus cosine x on an interval from 0 to 2. Again, same thing, we want to find the derivative. I'm going to pause this to save a little bit of time and come back with the derivative done. Okay, so we took the derivative of that function. So for the square root of 3 times sine, the derivative is square root of 3 times cosine. The derivative of cosine is negative sine. We set that equal to 0. A little bit of algebra, and we end up with sine x over cosine x equals root 3. Same thing as the tangent of x equals root 3. So the angles where the tangent of x is equal to root 3 are pi over 3 and 4 pi over 3. One thing to remember, critical numbers are where the derivative is equal to 0 or where the derivative is undefined. So tangent is going to be undefined at the spots where cosine is equal to 0. So if cosine of some angle is equal to 0, then we're dividing by 0. That's undefined. So cosine is going to be equal to 0 at pi over 2 and 3 pi over 2. 3 pi over 2. So putting those numbers on making a sign chart, we're going from 0 to 2 pi. I'm putting parentheses there because the 0 and the 2 pi are not included. And we're going to have pi over 3. We have pi over 2, 4 pi over 3, and 3 pi over 2. Again, we want to plug numbers into the derivative to find out if that's positive or negative. This becomes a little bit messy. The better you are with picking the values, the easier it becomes to evaluate the derivative. If we pick, for example, pi over 6, which is in between 0 and pi over 3, then we have root 3 times the cosine of pi over 6. With the cosine of pi over 6 is root 3 over 2 minus the sine of pi over 6 is 1/2. So we have 3/2 minus 1/2 is a positive 1. So our derivative is positive in that interval. For pi over 3 and pi over 2, there's not really a nice, neat, special angle to pick. But if we pick something super, super close to pi over 2, then the sine of pi over 2 is going to be 1. The cosine of pi over 2 is going to be 0. So if we're picking an angle very close to pi over 2, cosine, this term is essentially 0. This term is essentially 1. So we have 0 minus 1, which is going to be a negative number. Between pi over 2 and 4 pi over 3, we pick the angle, I believe pi would work well. Actually, pi is going to be nice and neat. So root 3 times the cosine of pi, which is negative 1, minus sine of pi is 0, gives us a negative root 3. Obviously a negative number, so we're going to be decreasing in that interval. For 4 pi over 3, 3 pi over 2. Again, not a nice, neat number to work with, but if we pick something super close to 3 pi over 2, the cosine of 3 pi over 2 is 0. The sine of 3 pi over 2 is negative 1. So we pick something super close to 3 pi over 2, we're going to have essentially close to 0 minus close to negative 1. We're going to be very, very close to a positive 1. The idea is we're going to have a very small number minus something close to negative 1. The idea is that we're going to be positive in that interval. And then between 3 pi over 2 and 2 pi, you can try 11 pi over 6. So you have root 3 times the cosine of 11 pi over 6 is root 3 over 2 minus, and the sine of 11 pi over 6 is negative 1/2. So you're going to have 3/2 plus 1/2, obviously a positive number, tells us it's increasing. So all said and done, this function is going to be increasing on the interval from 0 to pi over 3, and also from 4 pi over 3 to 2 pi. Again, 3 pi over 2, we don't have to pass over that number. 3 pi over 2 is okay in the original function. So original function does exist at 3 pi over 2. And then f of x is decreasing on the interval from pi over 3 all the way to 4 pi over 3. And we would have a relative maximum at x equals pi over 3. And again, the ordered pair would probably be better. So when x is pi over 3, we plug that into the original function. We have the sine of pi over 3. The sine of pi over 3 is going to be 1/2. And a cosine of pi over 3 is going to be, sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. So you have root 3 over 2 times root 3 plus 1/2. That's going to be 3/2 plus 1/2 is 2. And we have a relative minimum at x equals 4 pi over 3. Again, we know we have a maximum because our derivative changes from positive to negative. We know we have a minimum because our derivative changes from negative to positive. And again, the ordered pair there, 4 pi over 3, if you plug that value in to the original function, the sine of 4 pi over 3 is going to be a negative root 3 over 2. So you have root 3 times negative root 3 over 2 plus, and the sine of, back to original function, the sine of, or I'm sorry, the cosine of 4 pi over 3 is going to be negative 1/2. So that gives us negative 3/2 plus negative 1/2 is going to be negative 2. So those are the extrema, and these are the intervals of increasing and decreasing. I'll take a little bit of time here. For this example, we're given the derivative. So we can see the derivative is equal to 0 at -5, at 1, 6. Those are our critical numbers. We want to plug numbers into the derivative to find out if the function's increasing or decreasing. So when we're plugging into the derivative, keep in mind x minus 1 squared, that term's always going to be positive. So if we pick some number less than -5 and plug it into each of these terms, we're going to get a negative. Say it's -6 plus 5 is negative. The x minus 1 squared term is positive. If we do -6 minus 6 also gives us a negative. So all of a sudden we get a positive derivative. We pick 0 and plug it into each of those three terms. 0 plus 5 is a positive. Second term is going to be positive. 0 minus 6 is negative. So we end up with a negative derivative. If we pick, for example, 2, plug that into the first term as positive. Second term is going to be positive. 2 minus 6 is negative. That gives us a negative derivative. If we pick something bigger than 6, plug into each of those three terms, you're going to get positive. So critical values, we have a relative maximum at x equals -5. We have a relative minimum at x equals 6. And at x equals 1, that's neither a max nor a min because the derivative does not change sign. I'm going to pause, get this last example set up, and then that'll be it. Okay, for this last example, found the derivative. 2/3 times 9 gives us 6. Decrease our exponent by 1, so we have a new exponent of -1/3. And the derivative of x squared minus 1 is 2x. Multiplying the 6 and the 2x gives us 12x. And I'm going to rewrite x squared minus 1 to the -1/3 as a cube root of x squared minus 1 in the denominator. So for critical numbers, we can find where the derivative is going to be equal to 0. So if we have a fraction is going to be equal to 0 when the numerator is equal to 0. That gives us x equals 0. Critical numbers are also where the derivative would be undefined. If our denominator is equal to 0, then our derivative is going to be undefined. So we have critical numbers of 0, 1, and -1. Put them on a number line. We're going to do a sign chart. So when we plug into the derivative, just consider positive and negative. We plug a negative number into the numerator, that's going to be negative. If we plug something like -2 into the denominator, -2 squared is going to be 4. 4 minus 1 is positive. The cube root of a positive number is positive. And then if we do the same thing for the other intervals, if we do -1/2, negative in the numerator, -1/2 squared is going to be 1/4. -1 is a negative number. Cube root of a negative is negative. Negative divided by negative is positive. Put a 1/2 in there. Positive divided by negative. Negative. And if we put something above 1 in there, positive divided by positive is positive. So we know that at the critical value of -1, we have a relative minimum. At the critical value of 0, we have a relative maximum. And at the critical value of 1, we also have a relative minimum.